this video, we're going to look at what is known as weighted least squares. So previously in the linear regression course, we used what were called ordinary least squares. Sometimes we'll just abbreviate that to the least squares method for estimating a regression line. And so when we have things like non-consistent variance or outliers, it may require a different method for estimating the regression line. And so we're going to look at some other methods, in particular what is called weighted least squares. And so just to kind of recall what we have seen previously, remember from module 1 that you saw the following. And so it actually had you in the homework show that this piece right here, if I can get this to let me write, this piece right here was true, and previously we would just denote this vector as beta hat, but here we're going to denote it as beta hat OLS since we're going to see a different way to derive those estimates. So just more simplistically going back to review, what we mean when we say least squares is the idea of really what we're doing is if we have our data points, we're looking for the data points that best fits the line, or probably the line that best fits the set of data. And what we mean by best fit is it has the smallest possible sum of the squared errors. So remember that when we talk about an error, what we really mean is the distance between the fitted value and the observed value. So look at this picture right here. We have a very, very small data set. We had 1, 2, 3, 4, 5, 6, 7 data points in this data set. And so when we talk about an error, again, we're talking about that vertical distance between an observed value and a fitted value. So for example, if we look at this observation right here, the error would be the distance from that point to the fitted value, which would be the point that falls right along the line. And then we know that some of fitted values will fall above and some will fall below the line. So that's why we look at squared errors instead. And ideally, we want the line that makes the sum of all of these squares the smallest. So you can imagine there's an infinite number of lines that I could draw on this scatter plot. So for example, a line that wouldn't fit this data at all could be a line that goes like this. And so you could imagine if we were going to look at the squared errors for this line, they would all be huge. I'm not doing a very good job of drawing these, but you get the idea. So that's what ordinary least squares does. So instead, let's change our attention over to what is called weighted least squares. So the method of ordinary least squares assumes that there's constant variance in the errors, and so that's homoscedasticity. When that is violated is when we could bring in this idea of weighted least squares. So recall that we can express the value of the errors for all the observations as a column vector, and so we have that column vector here. And we've made this assumption that when we look at any of those individual errors, that they are going to be normally distributed. And the assumption is they're normally distributed with mean 0 and variance equal to sigma squared. So notice in this context, sigma squared does not have an I on it. In other words, all of the errors have the same variance or standard deviation. In other words, we have homoscedasticity. So if we wanted to, we could look at epsilon, the vector, instead. And what we would say is that epsilon is assumed to be multivariate, normally distributed, with mean vector 0 and constant variance covariance matrix. So here is what that covariance matrix would look like. And so notice here, along the diagonal here, we have sigma is the same, and then they're all independent of one another, so we have that the covariances are 0. The method of weighted least squares can be used when the ordinary least squares of assumption of constant variance in the errors is violated. In other words, you have heteroscedasticity. And so here we have the same model that we would have seen before, but notice that epsilon is now denoted with a star here. So what's different from what we had previously is if we look at that the multivariate normal distribution for that vector, Now, instead of having sigma be the same for all of the errors, we now see that the subscript on sigma depends on which observation we're looking at. So in other words, what we're saying is that now each epsilon I has its own sigma squared I. So this is why we say that it's heteroscedastic, they're not all the same. So we're not using that assumption of equal variance. Now that doesn't mean that some of them can't be equal to another. Like we could have sigma 1 is equal to sigma 2, and then sigma 3 through sigma n are equal to one another. So this doesn't say they all have to be different. This is just saying they're not all the same. So notice now each of those sigma squareds have a different subscript, and this is going to allow the variances to differ from one another. If we define the reciprocal of each variance as a weight, then we could define what's called a weight matrix, and it would look as the following. So each of these weights are going to be the weights that correspond to the individual errors. And so we could place those along the diagonal, and notice we are going to have 0 in the off diagonals. So with this setting, we can make a few observations. Since each weight is inversely proportional to the error variance, it reflects the information in that observation. So what this tells us is an observation with a small error in variance is going to have a large weight to it, since it's going to contain relatively more information than an observation with larger error variance. And the weights have to be known. And so we're actually going to look at some examples here where the weights are known and where they're unknown. But we do have to have known weights, or usually estimated, to a proportionality constant. And one thing to keep in mind is this isn't the only way to define weights, so we're going to look at a couple of different weights and what follows. So when we assume that we know those error variances, we could find the MLE of the regression coefficients just like before. And so in the reading that I have suggested for you, there's a little bit more information here, but what ends up happening is you see exactly what you saw up above for ordinary least squares. The only difference is that now those weights are included, and so you see those incorporated here and here. So let's look at an example with known weights. So consider the dataset statin, which contains simulated records on diabetic patients collected from 130 practices. And so these practices include hospitals, clinics, and other types of providers in Pennsylvania. The outcome variable here is going to be the average LDL cholesterol of the diabetic patients, and the explanatory variable is going to be the percent of diabetic patients at the practice who are on statin drugs. So notice here, when we think of these observations that we're looking at, each of these observations is going to represent a practice. So in total here, we have 130 dots. So the dots don't represent individual patients, they represent individual practices. And so our outcome variables here aren't going to be LDL for a single patient, they're going to be average LDL. And then on the explanatory, it's really going to be a proportion of the diabetic patients who are on statin drugs. So when we fit a simple linear regression model, we can see that the correlation between statin and LDL is approximately 10% and that it's not significant. However, notice that this model is treating each practice with equal weight. So in other words, it's saying in terms of the data and in fitting the model, each of these practices are equal to one another. But we know that since some of the practices are hospitals and some of them are really small clinics, that might not be fair, because some of them are going to have much smaller variability because there's going to be a lot more patients within that practice versus other ones. And so here, despite the fact that some practices such as the Philadelphia hospitals have nearly 2,500 patients, while the small rural clinics may only have 11 diabetic patients. So clearly the results for the large practices, they're going to be less variable because they're going to have more patients there. Whereas, the smaller ones are going to be more variable. And those that are less variable, we really should be giving them more weight in the model. So in particular, since the outcome in this case is an average, it's reasonable to weight the variance based on the number of patients in the practice. So here we're going to assume that sigma squared I is equal to sigma, which will be a constant variance divided by the sample size for that particular practice. And so that will give us a weight of Wi is equal to Ni. So let's talk a little bit about the sampling distribution of these estimates. So recall that the assumptions about epsilon are true, then for the ordinary least squares, we expect those estimates to be normally distributed here. And notice that we're not talking about the distribution on the errors here, we are talking about the distribution on the estimators. Approximately normal. We anticipate the mean of beta hat to be equal to beta, and so here when we have beta hat and beta, remember that we are talking about that vector where we have beta naught and beta 1. Oops, that should be a 1. And again, this is because we're looking in the context of simple linear regression. And then we've seen this previously, that here is the variance for that estimator. Now note that if we look at the weighted least squares, we're still going to have that linear combination of the yi's. It's still going to be normally distributed, but the difference is now that weight is going to be incorporated. And notice that the weight here is really what distinguishes these two from one another. And then it ends up that since those are in a similar form, that the derivation of confidence intervals in tests are very similar to what you saw in linear regression with ordinary least squares. So let's continue that example. So using weighted least squares, you can estimate the effect of statin. And so here are the new estimates with the weighted least squares. So we fit the model, it's just how we create these estimates is different from what we did before. And considering that heteroscedasticity, in other words, we know there's not going to be equal variability within those practices, we now have a highly significant test and more accurate estimate. And so this data was actually simulated with a true beta statin of -0.2. And then additionally, the weighted correlation increased from 0.1 to 0.24. So for this particular example, the weights were known. And there will be cases, like this one, that using some of that domain knowledge or knowledge about the data will indicate to us what a reasonable weight should be. And there are other circumstances where the weights are going to be known. And so here we have a couple examples of what that might be. So for example, if the ith response is an average of equally variable observations, then you could use a weight just like we did with this example. If it's a total of n observations, in other words, you're going the opposite from how you would go in an average, you would have 1 over Ni as the weight. And then if the variance is proportion to some predictor xi, then you could use that as a weight as well. But what about if the weights are unknown? So the preceding approach, known as weighted least squares or WLS, easily handles unequal variances for problems in which that relative variance of the outcomes are known. And one thing to note here is it was not necessary to know the actual variance, just the relative ratios to them. And so just like in that last example, we know that the relationship to one another was probably based on how many patients were in the practice. We didn't actually know the variances of each of those practices. So however, what about situations where the variances seem to increase with the mean? So that could be an example where we wouldn't know what the weights would be. Because here we don't know the means ahead of time, or otherwise we would need to fit a model to begin with, and therefore we don't know the appropriate weights either. So let's look at another example. So consider a study in which the investigator measured hand speed. And so this is going to be time it takes to remove a bolt from an S-shaped iron rod for a number of subjects at varying ages. So first of all, looking here at the data set, so here we have age, and here we have the time to remove the bolt. So looking across here, if we look right here, we can see that there were approximately 9 or 10 subjects, it looks like, that were right at 20, a few were at 21, and then, going on across here. So these dots really do line straight up with the ages on the whole numbers. Another thing to notice is down here in the 20s, if we look at the variability of these points versus the variability of those that are above 80, we can see that we have much higher variability in that speed for those that are older than 80 compared to those that are 20. So in other words, older individuals take longer to complete the task. The older subjects have more variability in their responses compared to the younger ones. We can also see that there is a slight trend upward. So in other words, older individuals are taking longer to complete the task. And this trend really isn't quite linear. We do seem like there's a little bit of a curvature in there. So roughly speaking, it appears the standard deviation is proportional to the mean, and therefore the variance will be proportional to the mean squared. So to see this relationship, we can look at the mean compared to the standard deviation for each of the 74 values of age in the data set. So moving from this plot to this plot, let's look at what we're doing here. Remember that along the x-axis you had these different ages, and it ends up, if you actually counted how many age sets there would be 74 different values that age took. Now for some of the ages, for example, at age 20, it looks like again there were about 9 to 10 observations. Some other ages have a fewer observations, some have a little bit more. So when we say 74 values of age, what we mean are those distinct values of age that were seen in the data set. Then, for each of those distinct values, what we did was found the mean time for that age as well as the standard deviation of time for that age. So you'll notice in this scatter plot here, oh, but I just realized there's an error. It shouldn't be 74, it should be 76. For these 76 age groups, there's one dot for each of them. And then for that age group, so for example at 20, for those 10 different times that occurred for people that were age 20, we found the standard deviation of that time and the mean. And so that's what is plotted here. And so looking at this plot, we can see the relationship, it's roughly linear, and the standard deviation appears to be proportional to the mean. So in other words, that rate of increase tends to be similar. So once we fit the model, we will have estimates from UI, and therefore that's going to give us an estimate for WI. However, once we change WI, we're going to change the fit, and therefore you change UI. So which then is going to change to WI. So really what you can see here is this is going to be a little bit of an iterative process. Each time we refit the model, we get a MUI, it's going to change WI. Those WIs, we refit the model, we get new MUIs. So this is what's known as iteratively reweighted least squares algorithm. And so how this typically works is you fit a model, which will obtain beta hat and mu hat. Use mu hat to recalculate W. Repeat those steps until the model stops changing. And so here is that example continued. One thing that I would really recommend doing is, just like the previous sets of notes, at the end of these notes, I do have the R and the SAS code here. I would really recommend, I think it's most obvious with the R code, go through this R code line by line and you'll see how that iterative process is working. So if you run that code, here's what you're going to find. So we have our original ordinary least squares estimates, and we have the weighted least squares estimates. Here we can see the corresponding lines on that original scatter plot. So note that by taking that heteroscedasticity into account, the slope is lowered somewhat as the regression line is less influenced by those highly variable points to the right. In other words, it takes care of the fact there was more variability in those older patients. However, by more accurately modeling the distribution of the outcome, the standard deviation of our estimate is reduced from 0.0018 to 0.0013. Now that's not a huge decrease, but it is nonetheless a decrease. And so consequently we obtain a larger test statistic, even though that estimate is close to 0, and our R-square has a slight increase. So this particular example, we don't see a huge change going from OLS to WLS, but we are still doing a better job. And it's important to recognize that this only improves our results if we model the variances accurately. So suppose that you were going to use iterative reweighting, but instead of, what we did up here, where we had to the -2, let's say we had accidentally instead looked at mu hat squared. Fitting this model, you would more than double your standard error and decrease r squared from 0.41 to 0.31. Right. And then finally, another thing that we could do is consider a quadratic fit. We can use ordinary least squares or weighted least squares, same here. And you'll see here the fits are actually very similar in this case, although once again we are going to achieve a reduction in standard error and improvement in r squared. So here's just a couple key points regarding weighted least squares. The difficulty in practice is going to be determining the estimates. That's always going to be the hardest part. Weighted least squares estimates of the coefficient will usually be nearly the same as the ordinary unweighted estimates. In cases where they differ substantially, the procedure can be iterated until the estimated coefficients stabilize. And then in cases where the values of the weights may be based on theory or prior research, and in designed experiments with large number of replicates, weights can be estimated directly from the sample variances of the response variable at each combination of predictor variables. And then the use of weights will legitimately impact the widths of statistical intervals. And that should be obvious because if we're changing the standard error of our estimates, that of course is going to impact any confidence or prediction intervals that we create.